Okay, maybe we should start. It's already 8:30. So welcome everyone. Welcome to the morning session for this talk. So our first speaker will be Sergey Alexandrov, who will talk about the modularity of Calabi-Yau threefolds. Let's welcome. So the talk will be 1 hour, and after that we can have a short discussion.
Thank you. And first of all, I would like to thank the organizers for inviting me to present my work at this remarkable congress. And I would like also to help all volunteers and people who help in the organization for very kind hospitality. I would like to present today the results of a series of works which I did with my collaborators, Boris Pilin, who gave the talk yesterday, Nala Gadam, Jan Scott, Sergey Alexandrov, Albert Clem, and my PhD student, Khalid Idris. Let me start from the introduction and explaining what this talk will be about. Let's consider type 2A string theory compactified on the Calabi-Yau threefold. Well, it's well known that in 4D, the effective theory is given by some n equal to supergravity, where we can define the so-called BPS indices. A rough definition of these guys, and they will be the main object of my talk. And what we should know about them is that they depend on electromagnetic charge vector, which is denoted by gamma, which has two B2 plus 2 components, where B2 is the second Betti number of the Calabi-Yau. Just because we have B2 plus 1 gauge fields in the effective action, and each gauge field gives 1 electric and 1 magnetic charge. And in the following, it will be convenient to represent this vector in components like this, where the index A runs from 1 to B2. And these guys, they have both physical and mathematical incarnation. So in physics, as Boris mentioned, they count the number of states of half BPS black holes appearing as solutions of this n equal to supergravity. And at the microscopic level, these black holes can be seen as bound states of D6, D4, D2, D0 branes, wrapping respectively 6, 4, 2, and 0-dimensional cycles of the Calabi-Yau. And this is why this representation is very convenient, because the components precisely correspond to D6, D4, D2, D0 brane charges. And on the mathematical side, these BPS indices are nothing else but the generalized Donaldson-Thomas invariants, which Boris briefly described how they are defined in mathematics. And on the mathematical side, this charge vector is nothing else but the Cherenkov. And it's a tremendous problem to compute these invariants, topological invariants of the Calabi-Yau. And whereas for non-compact Calabi-Yaus, there are plenty of techniques how this can be done, using quivers, localization, relation to subtopological theories. For compact Calabi-Yaus, all these techniques just don't work. And we need to find something else. And this is precisely my goal, to show you how they can be computed for compact Calabi-Yaus. Actually, I will be mostly interested in a particular set of these BPS indices, namely those which correspond to D4, D2, D0 bound states, which means that we set D6 brane charge equal to 0, no D6 branes. And then on the mathematical side, they are known as rank 0 DT invariants. Rank is precisely the D6 brane charge. And it's known that these BPS indices, they invariant under the so-called spectrum flow symmetry, which allows kind of reduce the dependence on D2 brane charge. So instead of the full dependence on the full D brane charge, they turn out to depend just on the so-called residue class, which takes just a finite number of values, namely given by the determinant of a certain quadratic form constructed from intersection numbers of the Calabi-Yau and the magnetic charge, which is just D4 brane charge. So in the end, they depend on this D4 brane charge and the residue class, and a certain shifted version of D0 brane charge. So it's convenient to introduce it because this combination stays invariant under the spectral flow symmetry. And therefore, we can denote them this way. And once we do so, we can form generating functions of these guys just by summing over this invariant 0 brane charge. And we can do this because this sum turns out to be bounded from above, because if you spoil this condition, the corresponding BPS index is known to vanish. In mathematics, this is known as Bogomolov bound of T there. And you see that here I introduce a little bit different notation, so omega bar, which denotes actually a rational version of this invariant. Actually, as Boris explained yesterday, in mathematics, it is these guys which are first, which I introduced first, and then it's only a conjecture that these guys without the bar are integer. But in physics, well, they must be. So we have this generating function, and I define generating function with the rational invariants, not the integer ones, because it is such generating function which is expected to possess nice model properties. Which model properties it has, I will explain a little bit later. Wait for 5-10 minutes. For example, in the simplest possible case, where D4 brane wraps the so-called irreducible divisor, which just means a 4 cycle which cannot be decomposed as a sum of other 4 cycles, the model properties are really easy. So in this case, this function must be the so-called weakly holomorphic vector-valued model form of this particular weight, where again B2 is the second vector now. And so let me briefly explain what these words mean. So vector value just means that we have a vector of functions where the components of this vector is precisely labeled by this index mu, which takes finite number of vectors. Yeah? Then weakly holomorphic means that we can expand it in the parameter q, which is just exponential of 2 pi tau as usual, and this expansion will contain a finite number of terms with negative power of 2. That's important, that such terms are present. And finally, that it's modular just means that it transforms under the standard SL2Z transformation of the parameter tau, such that, well, it transforms in covariant way, so there is the standard prefactor in the power given by the weight. And then here, since this is a vector-valued object, in general, we should rotate it by certain metrics, which is known as multiplier system. But it's a known object. It's just typically some phase factors, so it's completely fixed. We know it exactly. And now I will explain in one slide kind of the main message of at least the first half of the talk by Boris. Just to remind you what it was about. So what was the main message? So the point is that the space of this weakly holomorphic model forms is finite dimension and is bounded from above by the number of polar terms. So the terms which have this power of q, which is negative. And due to this, it means that it's sufficient to find these polar coefficients, and we can completely fix our generating functions. And we developed a certain machinery to do that, which starts from the direct integration of topological string, which produces, let's say, tables of Gopal-Kumar buffer invariants. Then we can apply MNOP formula and extract from these GV invariants Thomas invariants. And then there are some nice wall-crossing correlations which allow to convert these invariants to our rank 0 DT invariants, so D4-D2-D0 BPS indices. And typically we can compute some finite number of these guys, and for some one-parameter Calabi-Yaus, we were able to compute all polar terms and even some more terms. And in this way, we can fix the corresponding generating functions exactly. And at this point, we can go back, we can expand this function, get infinitely many rank 0 DT invariants, apply the same wall-crossing formulas in the reverse direction, get new PT invariants, new GV invariants, and these guys will serve as new boundary conditions for the direct integration method. And this way we can bypass the limitations of this method for solving topological string. And this is what has been done actually. But at this point, the question arises, can we actually extend this approach beyond this case of reducible divisor, which essentially means that D4 brane charge is equal to 1? Can we generalize it to arbitrary D4 branch charge. And this is precisely the topic of my talk. So the plan will be the following. So first, I will explain you the origin of the modular properties of the generating functions of zero DT invariants and where they come from and how they look like. Then I will consider the simplest non-trivial case, which corresponds to just usual mock modularity, or if you wish, this is D4 branch charge equal to 2. So here we have exact results for generating functions. I'll explain how they can be obtained. And then in the second part of my talk, I would like to consider even a generic case, generic D4 branch charge. Here we're still unable to get the generating functions, but we can at least solve the so-called anomaly, modular anomaly equation in terms of indefinite theta series. And I would like to explain how this can be done. Okay, so let's start first of all answering the question why we expect at all that these generating functions should possess any modular properties. Because typically you expect modularity where there is some torus in the game, but well, we have just typed in on Calabi-Yau. In principle, there is no any torus, so you can ask where the modularity comes from. So let me explain. Okay, so as I said, we do have type 2 in Calabi-Yau, but this is the same as M theory in Calabi-Yau times the circle, yeah? And let's compactify this setup on an additional circle. So of course, then we get an effective theory which is already in 3 dimensions. And in 3 dimensions, because all fields can be dualized to scalars, the effective action can be written as a certain nonlinear sigma model with some target space which I denote by M. And now you see that we already on the M theory side, we have product of the circles, which is nothing else but the torus. So it means that we do have a modular group in our story. And the claim is that the modular symmetry of the torus should be reflected somehow in this effective action, and it's known how it is reflected. Namely, this target space M must carry an isometric action of this modular group. So that's the requirement where the modularity appears. And the same conclusion you can get if you apply just the usual T duality along this circle here and go to type 2B, and then this modular symmetry is nothing else but the S duality of the type 2B formulation. And then you can also recognize this target space M as just the usual hypermultiplet modular space if you compactify type 2B on Calabi-Yau. So you can forget the circle in this case, and this space M is the same as hypermultiplet modular space in this one. But now, let's recall that what we're interested in are D4 branes wrapped on a 4 cycle. Yeah? But D4 brane has 5-dimensional wall volume, so we still have 1 dimension, not compactified. So let's wrap it on this additional circle, which we added here. So from the space-time point of view, we will get some point-like object, which is, and point-like objects in space-time correspond to instantons. So this means that the metric on our target space M will receive instanton corrections from these objects. And it's natural to expect that each instanton correction will be weighted by the BPS index omega, just because these guys, they count the number of such objects, essentially. And in fact, we do know the explicit form of all these instanton corrections, because already 15 years ago, we managed to incorporate them using certain twistorial construction, which I don't have time to explain, but it's known how to do. So we know the explicit form of these guys, the explicit form of the instanton corrected metric on M. And on the other hand, you see, we have this restriction that M must carry an isometric action of the modular group. But it's clear that for arbitrary values of BPS indices, this will not be true. So these indices must be tuned in a very specific way so that SL2Z is a modular group, is an isometry group of the metric. So which means that this isometry restriction imposes certain condition on these BPS indices, almost precisely on the generated functions. And it's actually very non-trivial and remarkable that it's possible to, because this condition sounds a little bit abstract, but it can be made very, very precise. So one can actually extract this condition in terms of some equation. And this is what I'm going to show now. So this restriction turns out to demand the following property, that this particular combination of the generating functions, you see our generating function appears here, and then here there are more generating functions. So this particular combination, which is a non-homomorphic function of tau and tau bar, must transform as a true vector-valued modular form of the same way. So this is the condition which follows from the isometry condition. Well, the sense of this expression, which might look complicated, is actually not so complicated, because what you do here, you just sum over all possible splittings of D4 branch charge into components. And then you take the product of the generating functions corresponding to these components. Of course, the most non-trivial piece is this coefficient R, which sits here, which depends on all these charges, and is a non-homomorphic function. I don't have time to explain how it looks like, because it will take, I don't know, 15, 20 minutes just to explain all the ingredients which enter its definition, but we know its expression exactly. So it's a known function. And in words, it's given by certain non-homomorphic indefinite theta series with some non-trivial kernel constructed from the so-called generalized terra functions. Actually, they appeared already in one of the talks yesterday, but I will briefly introduce them later in my talk. Just at this point, you can, well, just it follows from the name that these are certain generalizations of the usual error function. And yes, precisely, because these splittings precisely correspond to decomposition into constituents, which happens due to wall crossing. Yes. Okay. And then another comment just here, that you see that the sum over n is, well, it's clearly it's restricted by the number of irreducible components we have in our divisor, and I will denote this number in the following by small r. So it's not infinite sum, it's finite. Okay, and mathematically all this means is that if the divisor is reducible, which means that n max is larger or equal to 2, then there is this term, which means that this function is not modular. It has a modular anomaly, but this modular anomaly is cancelled by this second term. And in this case, we call this function h hat the modular completion of the original function, and the original generating function is nothing else but a mock modular form, or more precisely, high depth mock modular form, where the depth is determined by this small r. And for those who don't know what is mock modular form means, this is a brief reminder. So this is a holomorphic function which does has a modular anomaly, but this of the very special type. So such that it's controlled by another modular form, which is called shadow. And it's controlled in such a way that this particular combination, which is precisely the modular completion, transforms as a true modular form. And then G is this shadow. In fact, in physics, in most cases, we have a slight generalization of this guy, the so-called mixed mock modular form. So in this case, the shadow is not just one modular function, holomorphic modular function, but it's a product of two functions. One is, both of them are modular, but one is holomorphic and another one is anti-holomorphic. Or we can take some of such products. It's also possible. And if we want to talk about high depth mock modular forms, it just means that for example, the depth n mock modular form is such that its modular anomaly is controlled by depth n minus 1 mock modular form. So it's a kind of iterative definition. So in this case, the usual modular forms have depth 0, usual mock modular forms have depth 1, and so on. Okay, so from now on, let's just for simplicity restrict to the one modulus case. The idea, so the wall crossing in this story appears, So for this, I should explain how this restriction was derived. But roughly speaking, the idea is the following: that in the original, so there is certain function which must be modular. We know expression for it, and then this function depends on BPS indices. But those BPS indices are evaluated in an arbitrary, not arbitrary, at some point in the modular space. But the BPS indices which we consider, I didn't mention that, but actually these are those which are evaluated at the large volume attractor point. So what we should do, we should express our the original BPS indices through those which are evaluated at the large volume attractor point. So this is at this point you use this Denev's attractor flow conjecture. So and this when you substitute this expression in terms of attractor flows, well, it's it originates from wall crossing, yeah. But the how many walls you cross, well, in general, arbitrary number, but not more than you can decompose the original divisor. How many components? This is where these decompositions come from. Essentially, they come from this Denev's attractor flow formula. Well, the holomorphic piece is just generating function of BPS indices evaluated at the large volume attractor point. Well, yeah, sure, yeah. Well, it depends from which point of view you look, because from this point of view, it's kind of due to wall crossing, because wall crossing kind of spoil modularity, and to restore modularity, well, the usual story. You restore modularity at the price of holomorphicity. That's the usual story. Or you can think in terms of wall sheet, for example, then the reason will be the presence of certain continuous spectrum in the game, which again, the reason for non-holomorphicity. Well, I'm not sure. Well, it's no, it's not a polynomial, so it's not polynomial. So here the non-holomorphicity, well, essentially it's exponential. It's in the in most contributions it's in the exponential. It's like having the Ziegel theta series, for example. Yeah, I will do this. It will be holomorphic anomaly for the completion. Yes. Okay, so let's consider the most simple non-trivial case. Yeah, but first of all, I would like to restrict to this case of B2 equal 1, so one Kähler modulus, just for simplicity. In principle, many things which I'm going to talk about can be easily generalized to arbitrary case, but for simplicity, let's consider this one. And then in this situation, the D4 branch charge is nothing else but the degree of reducibility. So in the therefore in the following I will use this variable r instead of. And let's consider the simplest non-trivial case, which is r equal 2. So, and in this case, the requirement is that our generating function is a mixed modular form. So the depth is equal to 1, the weight is equal to -3/2, and its completion must satisfy this very simple holomorphic anomaly equation. So how it's written? Well, you see the two factors of H1, just because the only decomposition of 2 is 1 plus 1, yeah? And instead of our coefficient r, so what appears here is essentially the derivative with respect to tau bar of that coefficient r. In this case, is just this simple theta series labeled by the parameter kappa, which is for me is the intersection number of the Calabi-Yau, which in this case is just a number because B2 is equal to 1. And this vectorial index mu, it takes 2 kappa vectors. And the problem is to find function h which for which completion satisfies this anomaly equation. And the difference, big difference with the case considered by Boris, is that we have a mixed mock modular form. And if it was just mock modular form, then the polar terms would still be enough to fix our function completely. But for mixed mock modular forms, this is not true. So how do we should we proceed then in such situation? The idea is to proceed in two steps. So at the first step, let's just find some mock modular form satisfying this anomaly equation. Then, of course, if you add any modular function, it will still satisfy that anomaly equation. So it's a modular ambiguity. It's like solving holomorphic anomaly equation in topological string. And then the idea is that this guy already can be fixed by computing the polar terms. Because if you compute polar terms of these guys, so you know polar terms of these guys, you subtract and you get polar terms of this, and this is usual modular form, so it's completely fixed by polar terms. And the first step in this case is very easy, because if you look at this equation, it's immediate to guess the ansatz which you should use to find this anomalous piece. So it's just this one, where some new function g capital appears, but it's easy to see that it follows from this equation that capital G should be already usual mock modular form with completion satisfying even simply anomaly equation. So it's just, you see, proportional to this theta series. And in fact, precisely the same problem was considered in the famous paper by Double-Car, Murti, and Zagia, where they considered black holes in n=4 supergravity. So we can just borrow the solution. There is nothing to do. In fact, what they did, they constructed precisely such mock modular forms with the additional condition that they have a slowest growth of their Fourier coefficient. We do not care at all about this condition, but why not to take it's a solution of our problem, so we can take it. Any solution will suit for us. So, and the construct solution is a certain linear combination of some Hecke-like operators acting on certain kind of seed functions. Each seed function appears as soon as kappa is equal to square-free integer with even number of prime factors. So this Möbius function should be equal to 1. So you see that they appear for 1, 6, 10, 14, and so on. And in their paper, they computed, they produced, first of all, these Hecke-like operators. They also computed these functions, so everything is known. And just for the following, it will be useful to remark that Q1, which is, by the way, completely sufficient to describe all cases where kappa is a power of a prime number, for example. It's Q1, then it's, you shouldn't consider other seed functions. So in this Q1 is one of the most standard objects in the theory of mock modular forms. It's the generating a series of the so-called Hurwitz class numbers, and this is the same as the generating function of SU2 Waffer-Witten invariance on P2. So this will be useful in the fall. And so we completely solved in this way the anomaly equation, and then what remains to be done is just to find the polar terms. And for this, again, we can use certain wall-crossing formula derived by Sergey Alexandrov. And the idea is that there is a formula which expresses Potripande-Thomas invariant with certain conditional charges in terms of other PT invariants and D4-D2-D0 BPS indices with D4 branch charge either equal to 1 or equal to 2. And this is precisely what we need. Because if we impose certain additional conditional charges, then we can ensure that this term, with moreover q prime and prime equal to 0, so that this guy is equal to 1, is always present. And then we can put it to the left, this term to the right, and we get an explicit formula for this charge 2 BPS index in terms of other invariants. And in this way, we can compute polar terms in our generating function. Just the only problem is that this formula involves PT. So if you try to apply it, for example, for our set of one parameter Calabi-Yaus, the PT invariants which appear depend on sufficiently large D0 brain charge. And to compute such invariants, we need to know GV invariants at very high Gs. And for most of Calabi-Yaus, unfortunately, we don't know that. We're not able to compute. So direct integration of topological string is not enough yet to do that. But nevertheless, there are two Calabi-Yaus for which we can compute all polar terms. So this is the so-called decantic and quintic. So you see they have very small intersection numbers, 1 and 2. Typically, the less intersection number is, the kind of the easier the problem. In this sense, quintic is not the simplest Calabi-Yau. So the simplest one is this decantic. And for these guys, we computed all polar terms, and hence we found the generating functions for charge 2. So let me just flash the results for this decantic. So the first line is actually the result which Boris showed in his talk. So this is a generating, so the very simple generating function, modular function. So if you expand it, so you get this expansion. So here in blue, I showed just the polar terms. In this case, there are just 2 of them. And well, this is actually a result which was obtained some years ago, but we confirmed it in low cost. And the completely new result is this function for charge 2. Well, the first 2 lines correspond to this modular ambiguity fixed by the polar terms. Well, you see some crazy expressions, but this is just because this modular function is expressed in some, let's say, almost random basis, which is not kind of tuned to describe this function. So of course, in this case, the coefficient will be some crazy numbers. That's natural. But then the most important term is this one, the last. You see, it is this term which is responsible for the mock modular behavior of the function, and it's described in terms of these Hurwitz class numbers. And you can expand just all these functions, and in this case, H is a 2-dimensional vector. There are 7 polar terms, and using wall crossing, we computed actually all these terms, not only polar terms. And there is a remarkable match between this computation and the one which follows from the by expanding this crazy expression. And it's really beautiful to see how two completely different calculations match on the nodes. And at this point, let me do just a couple of remarks. So first of all, I believe this is the first example of a mock modular form which is assigned to a Calabi-Yau without any additional structure, something like T3 or elliptic fibration. I don't know any other examples of that. And second, which actually was mentioned by Boris also, is that from the mathematical point of view, so here we clearly see that there is a striking confirmation of the modularity, which in turn we derived it, as I explained, from S-duality of string theory. But from the pure mathematical point of view, there is no any explanation of why these generating functions should be modular. I think this is a very remarkable problem to understand where this modularity comes from, just from pure mathematics, without involving S-duality. So at this point, if there are any questions, please ask, because then I would like to proceed to a more complicated case of arbitrary charges. Well, if there are none, so let's proceed. So now I would like to address the point, what happens for even high charges, for arbitrary default brain charges. So here I just copied the same expression for the completion which I had before, just specialize it to the case of one modulus. And the idea is the same. Let's just use the same 2-step procedure. So we first find some mock model form. In this case, it will be of depth r-1, which should satisfy this anomaly equation. Then we will fix the modular ambiguity by computing the polar terms. But as I explained, it's to compute the polar terms is a really complicated problem. So the idea is, let's postpone it. Let's not do this at this point, but let's just try to at least to solve the mock model, this anomaly, find this mock model form. But let's try to do it for arbitrary charge. But then we have immediately a problem, because the anomaly equation which fixes this function involves generating functions for low charges, and these functions involve their modular ambiguities, which are supposed to be fixed by computing polar terms, which we haven't done. So in other words, our anomaly equation will involve some unknown functions. Well, what should we do then? Well, it's clear, then it just means that we should express this, the best thing which we can do is to express this anomalous piece in terms of these unknown functions and just find the coefficients. And the claim is that there is a natural ansatz for our anomalous function. So essentially you take the same equation, same expression as here, just replace h by h0 and replace these coefficients r by some new unknown coefficients, which we call anomalous coefficients. And the problem at this point is whether we can find these functions or not, these anomalous coefficients. If we find them, then we have an expression for the anomalous part, and what remains to be done is just to compute the polar terms. So then we will reduce the problem completely of finding generating function to finding just a finite number of terms in the expression, and that's it. Okay, but what is the restriction on the anomalous coefficients? Well, it's easy. Well, you just plug in that ansatz in the anomaly equation, and you can easily see that these guys, they should be depth n-1 modular forms, where n is the number of charges here. So the number, so index I runs from 1 to n, and the completion must have the following expression. So again, it's fixed in terms of g's for lower charges. Well, this expression is a bit different than the previous one. If before we summed the overall decomposition of our D4 branch charge into constituents, here you do the opposite. You sum, so you have a set of charges, and you sum over a set of groupings of these charges into subsets. Or in other words, you can, through such a picture, this sum is equivalent to the sum of a trees of depth 2 with n leaves. And these trees differ just how you group the charges together. And then to each node, here you associate a factor given by this anomalous coefficients, so they appear here. And to the root, you associate the original coefficients R. And the charges S are just given by the sum of charges which correspond to leaves connected to this node. So I think it should be clear, the structure. And if, by the way, we can have subsets consisting from one charge. In this case, the corresponding factor is just by definition equal to the chronic reciprocal. And just to give you an example, so the first two cases, so when the n equal 2, we have just this simple equation, and when n equal 3, we have this. So this term corresponds to this situation. So in this case, there is no coefficient r because it's equal to delta, so similarly to this one. In this case, there are no factors of g because they're equal to delta. And here we have, well, r depending on two charges, and g corresponding to this node depending also on two charges. So it should be clear, the structure. Okay, so now, can we solve this crazy anomaly equation and find these anomalous coefficients? So let's again start from the simplest case of two charges. Well, here it's very simple. There is nothing to do essentially, because again we compute the modular anomaly, holomorphic anomaly for this coefficient, and it's proportional to this. We know that it's proportional to this theta series, but now with parameter given by certain combination of charges r and kappa. Of course, if you take r1, r2 equal 1, then this reduces to the usual kappa, but generically it's, well, it will be different. And from this equation, we immediately can conclude that our anomalous coefficient is proportional to the DMZ modular form of optimal growth. This is a possible solution in our case. So there is nothing to solve. And now let's note, well, I already mentioned this actually, that if we take all charges is equal to 1 and also kappa is equal to 1, then this effective kappa 0 is also equal to 1. And in this case, this anomalous coefficient is the same as generating series of Curvis plus numbers. And this guy, as I already mentioned, is nothing else but the normalized generating function of SU2 Vafa-Witten invariance on P2. And in fact, this is not the claim, this is not an accident. Because there is a more general statement that if you consider anomaly equation for anomalous coefficients where all charges equal to 1, but you take n charges, and also you set kappa equal to 1, the resulting anomaly equation is exactly the same, well, up to some stupid normalization factor, as the anomaly equation for the normalized generating function of SUN Vafa-Witten invariance on P2. And so from here, you can immediately conclude that these two functions should be proportional to each other. Well, and there is just some relative normalization factor appearing. Okay. And that's it. So you see already almost doing nothing, we get two infinite classes of solutions. One is for arbitrary two charges, and another one with arbitrary number of charges, but all equal to 1, also kappa equal to 1. Actually, they are the same, kind of the same equations, almost the same equations as this, because what you can do, you can actually, the claim is the following, that the anomaly equations for Vafa-Witten, they come from the equation which I showed. Why? Because you can get this generic equation for rank 0 DT invariance, this equation for the completion. Why? Because you can Vafa-Witten invariance on the surface are the same as D4-D2-D0 BPS indices for a non-compact Calabi-Yau. Yeah. And the claim is that although the original setup has been derived for compact Calabi-Yau, where everything is non-degenerate and so on, actually it's much more general. Because it turns out that it also holds for some situations where, for example, quadratic form becomes degenerate. It also holds when you take the limit of non-compact Calabi-Yau, and this way you establish link with Vafa-Witten invariance. It also holds even if you introduce refinements. It also holds if you even go to high supersymmetry, and you can actually derive DMZ mock modularity from this equation. So it's really very, very generic and very powerful. And by the way, using these equations, for example, I was able to derive Vafa-Witten invariance, the refined version, for for arbitrary rank for all kinds, like Hirzebruch, Dilpetz, and P2. Well, sometimes reproducing all the results, sometimes getting it. So they all follow from this equation. Okay, and here I wanted to say is that, okay, so we have these two infinite classes of solutions, so it's natural to try to generalize them and get more general ones, but the problem is it doesn't work. We really worked really hard on that, but it doesn't work. At least we were not able to do it. And therefore, if we do want to have a generic solution for generic charges, we need to find something else. And the idea is that one can get general solution if you try to work in terms of indefinite theta series. And this is very natural because, I mentioned that these coefficients R, capital R, which control the anomaly, they are some indefinite theta series. And from this point of view, it's natural to look also for a solution in the same setup. And also, for example, solutions for Vafa-Witten, they also written, they can be written in terms of indefinite theta series. So at this point, let me remind you a few facts about indefinite theta series, which are very useful in practice. So first of all, just general definition. So I call indefinite theta series such a sum over certain lattice, where I have my parameter q to some power, qk, where q is some indefinite quadratic form. Indefinite means that it has a split signature, some number of pluses, some number of minuses, and then generically I must introduce also certain kernel here, which depends on this lattice vector k. Now, if I don't introduce this kernel, then my indefinite theta series is just not defined because it diverges due to the presence of negative directions. Yeah, so I do need some kernel which will ensure the convergence. And there are essentially two canonical ways to ensure this convergence. So one way is just, well, just introduce some damping factor which will suppress these negative directions. So for example, I can introduce exponential, which depends on this negative part of the quadratic form, yeah, and it will suppress the growth of this factor. And this is how you get Ziegel-Theta series. But note that here I have in the argument square root of 2 tau 2, where tau 2 is the imaginary part of tau, and of course it appears as a factor here when you substitute x by this. So what you get some model of, actually the Siegel model form is known to be, Ziegel-Theta series is known to be modular, but it will not be holomorphic because of this tau 2 appearance. On the other hand, there is a way to get a holomorphic indefinite theta series. For this, you take this kernel to be given by a product of differences of signs like this. And then if you impose certain conditions on these vectors here, vi, then one can show that this factor can ensure the convergence of this theta series. And now it is holomorphic. Because in this case, okay, of course, you replace x by this, but the square root of tau 2 is all this positive, so it's cancelled in the sign function. So nothing depends on tau 2 in this situation. So it's holomorphic, but unfortunately it's not modular, because these signs, they spoil modularity. And in fact, this is the canonical example of a mock modular form, which in this case has depth n minus 1, where n minus, where n minus is the number of minuses in the quadratic form. And at this point also, it's the natural question: can we construct a modular completion for such indefinite theta series? And the answer is yes. Actually, the recipe is extremely simple. The recipe is the following: just expand this product of differences. Just expand. So you get some sum of monomials, where each monomial is a product of sign functions of this form. Yeah. And then the recipe to construct completion is just replace each such product by the so-called generalized error function of rank n, where n is the number of factors here, which depend on all these vectors. And the generalized error function essentially is just this product of signs convoluted with the Gaussian kernel. And as I mentioned, the generalized error functions also appear as building blocks of our coefficients R, control internal. So this is why it's natural also to look for our solution in terms of indefinite theta series. Now let me show how this can be done in the simplest case of two charts. I believe that this is really instructive to see how this works. So this is the equation which we need to solve. So how do we solve such an equation? So in this case, R is roughly given by indefinite theta series of this form. So here quadratic form has 1 minus. So we have, and then we have the following expression. So we have E1. So this is the usual error function evaluated on certain scalar product where V is some vector. And then we subtract the sign here. And as a result, one can show that this is essentially exponentially suppressed, exponentially decaying expression. And now we should look for G such that this sum is modular. Well, then it's clear what to do. According to our recipe, if our theta series is written in terms of kernels defined by error functions, it will be modular. So what we need to do is we need to cancel this sign. So therefore, let's just write G as an indefinite theta series with the kernel given by the sign. But if you write this like this, it will be divergent. So you need, for convergence, you need a difference of signs. So you need to add a second sign function. But if you add second sign function to get something modular, you will have to replace it by error function. Whereas if you just take this sum, there is no error function. So what to do? The way out is to take this vector to be null. Why? Because you see here we divide by the norm of the vector. So if the vector is null, its norm is 0. So the argument is infinite. And for infinite argument, the error function reduces to a sign. So we do not need to complete kind of this sign. It's already modular, if you wish. So therefore, the claim, this is a solution. This is a solution for two charges. But unfortunately not, because in our case, we have, you remember, one modulus Calabi-Yau, so our lattice is just one-dimensional. Well, it's actually like this. And one-dimensional lattice doesn't have null vectors. So what to do? Well, actually the way out is to multiply by some number of Jacobi theta functions. And so we multiply the original equation by some powers of this Jacobi theta function, and then replace the function superior here by some g check, and consider this as a new equation. And the point is that due to this multiplication, the kind of we get an effective lattice which is extended. So each factor by theta 1 extends the lattice by one dimension. So we get some huge lattice, but with indefinite quadratic form, and it already has null vectors. And what is important is that this multiplication doesn't change the residue classes. It doesn't affect them. So for the new lattice, the residue classes are still the same as before. That's important. And more generically, for arbitrary charge, okay, we have, so for arbitrary charge, our lattice is like this, and then we multiply by some number of, again, Jacobi theta series. And the idea is that we get some new equation for new functions g check, and which, okay, they will depend on some number of additional z variables, elliptic variables, but that's fine. And we solve then this equation, so find g check in precisely this way. And then there is a procedure to get back the original function, the original solution. Just can apply certain modular derivatives on the solution, put all these extra variables to 0, and one can show that this is the result is some modular form. Okay, so it looks like we found a way to find a solution. But again, no, there is a problem. The problem, so to solve this problem, we actually need to introduce the refinement. So refinement means that we introduce certain additional variable z, which actually physically corresponds to some switching omega background. Well, for compact Calabi-Yau, this doesn't make much sense, but consider this as just mathematical trick. So we introduce certain variables, so our functions will now depend on this additional variable, and the claim is that we should look for solutions which behave like mock Jacobi forms. So this variable will be like the usual elliptic variable of Jacobi forms. And why should we do that? There are two reasons. First of all, this refinement, it turns out you could think that you introduce additional complications, but actually no, because this refinement simplifies a lot these coefficients are. Actually, the expression which I showed for R2 on the previous slide was the one for the refined case, because in the unrefined it's a little bit more complicated, so I cheated a little bit. And but the most importantly, the refinement regularizes certain divergences appearing due to the presence of null vectors. To see how this appears, let's consider the following so first of all, let's expand our vector in the basis given by these vectors v and w appearing in our story of the previous slide, and then there are some orthogonal directions. So w, I remind you, is a null vector. And let's consider sublattice where we set this orthogonal component to 0 and consider those vectors which have scalar product with w equal to 0. Well, then it's clear that kv should be 0, but we still, so our vector k just becomes kww, and therefore its square is equal to 0. So it's also null. Therefore, if we consider a part of the theta series given by this sublattice, well, the summand reduces just pure sign. And clearly, such thing is divergent. So as soon as you have null vector, you have a divergence. But if you introduce refinement, it amounts to, first of all, introducing this factor y to some power. Y is just exponential of pi as z. And also, one can show that you must shift the argument of one of the sides. And if you consider the same sublattice, what you get, well, it's easy to see, you get certain geometric progression, which is perfectly summable function. Yeah? It's convergent, and just the price to pay is that, well, at z equals 0, it contains a pole, but which precisely corresponds to the origin of divergence. Yeah, it's but for z not equal to 0, we have perfectly convergent function. So what do we get? I'm almost at the end. So in the end, we get a problem where we must find a mod Jacobi form on certain extended lattice, which such that it's regular at z equals 0. Why? Because in the end, we want to take the unrefined limit. We want to put z equal to 0. And the claim is that this problem has a general solution. So there is a general expression which can be written in terms of some theta series with kernels given by the standard form, which you should recognize. It's just a product of differences of signs. Now on this extended lattice, and just the problem is that these theta series, if I consider them alone, as I just explained, they contain poles in Z, and I need some regular function. But you remember, I'm solving certain anomaly equation, and as usual, this when I solve it, I have this holomorphic modular ambiguity. So in this case, it's represented by certain Jacobi forms, so I can use this ambiguity to actually cancel the poles in Z. So I just introduce these additional functions, and tune them to cancel the poles. And it turns out that they can always be chosen in this very simple form. And so in the end, I get a solution which is perfectly, it satisfies the anomaly equation, it's regular at z equals 0, and the problem which remains is to extract the unrefined limit. And somehow it turns out that if I want to do this analytically, this is the most non-trivial step. It's very stupid. To take the limit turns out to be quite complicated. And nevertheless, we realized it for arbitrary 2 and 3 charges. I don't show the expressions because they're a little bit cumbersome, but we do have them. So some explicit expressions for these anomalous coefficients. So let me just go to the conclusions. So there are 3 main messages here. So first of all, we derived modular properties of generating functions from the 0-dt invariants. We know them exactly, and they're quite general. They describe many objects. And using these properties, wall crossing and direct integration of topological strings, we were able to compute for some one-parameter Calabi-Yaus these generating functions exactly. And in particular, these provided the first examples of mock modular forms associated to these Calabi-Yaus. And it's important also that from these results, we can extract new boundary conditions for the direct integration. So we can bypass the limitations of the original approach. And in the second part of my talk, I also explained how one can address the same problem for high charges, larger than 2. And in this case, okay, we still cannot compute the polar terms, but at least we can solve exactly the modular anomaly. And there are, for some cases, there are several solutions. You remember I mentioned solution in terms of DMZ, in terms of Waffa-Witten, and now presented this indefinite theta series solution. And one can show that all of them consistent in the sense that the difference between different solutions is just usual modular form. So there is no problem. And once we know these solutions, the whole problem of computing the generating functions reduces just to finding a finite number of terms, these stupid polar terms. And of course, there are many possible directions to extend these results. Well, first of all, of course, it would be great to find a way to compute polar terms, especially for high charges. But probably we do need some new strategy. Maybe new, because these wall crossing formulas, which we have so far, they require knowledge of GV invariants to very high G. So maybe we should find some new wall crossing relations, or maybe something completely different strategy. I don't know. But one should think in this direction. So then I presented results for Calabi-Yaus with 1 Keller modulus, but very easy to generalize them to arbitrary number of moduli. So maybe it's worth considering some concrete examples and try to compute them. Well, one can consider kind of degenerate cases, which correspond to elliptical K3 vibrations. So K3 vibrations can be, well, some partially were presented by Boris. Part of the problem was addressed, but there are more things to study even in this case. And maybe one can say also something about DT invariance for higher ranks. That would be really interesting. So let me stop here, and thank you very much for your attention. Yes.
In fact, you can also recover Donaldson invariants of surfaces with positive geometries, D2 class one, free general.
I'm not sure because they contain this instant contribution. Monopole contribution. Yeah. I'm not sure because they don't fit this framework. Well, if one finds some, I don't know, duality or whatever, which relates one to another, then maybe, but otherwise, I don't know.
Cases, it's not modular. Right. It's
yeah.
Purely holomorphic, right?
Yeah. But then there is this addition.
There's even more contribution.
This monopole contribution.
I see. So which makes it
yeah. So maybe if it has some interpretation, like, so maybe if one can. No, I thought. I want to say that maybe the full generation function is like our completion, where. But this is not so. No. It should be something else because the function is holomorphic. Yeah. So whereas our completion is not holomorphic. So this should be something else. But
for example, for K3, you get for the elliptic genus, you get this n, that the R five things, you get the symmetric product, right? Is there any progress in obtaining the corresponding 2D behind this? Like using some localization of fiber or something like that?
This is a great question. Now, from the bullshit point of view, this is not understood. This is an open problem. Where this, well, it's kind of qualitatively, it's clear that modularity should come from some continuous spectrum, the bullshit, but to derive it precisely, rederive this equation for the completion, this is completely open. Yeah. There is a paper by Boris, yeah. For Wafavita. For Wafavita, yeah, but not for generic Calabi-Yau.
So
so in that, what happens in that case is that, kind of certain direction in the lattice decoupled because Calabi-Yau becomes non-compact. So the direction related, so the way to take the, so you consider some elliptic vibration over a surface, for example, and you take the limit of a large elliptic fiber. This is how you get Wafavita, for example. And then the directions related to the fiber, since the fiber becomes infinite, so they kind of decouple from the charge lattice. And well, I cannot say that this simplifies the story, but just you can compute this thing. So you can compute the data relevant to this thing. Well, maybe I didn't understand the question. In the case of Wafavita, yeah, that's possible. Well, no, I'm not sure that for general, no, for general, I'm not sure. But to be fair, this problem hasn't been really addressed. Nobody tried. So maybe, yeah, if one tries, that's possible, but I'm not sure. Generic, yeah, it will be.
Further questions? No, let's thank the speaker again.